In this video, I will review polynomial functions, and I will review them according to the plan that we developed in one of the previous videos called precalculus review. First, we're going to review the prerequisites, and then we'll review the answers to the following questions. If you need a reminder on what are these questions all about, please watch that video called Precalculus Review. Now let's get started with the prerequisites, and first let's discuss the operations. And here's the list of arithmetic tasks that are common when it comes to polynomial functions. So as you can tell, we have to be able to evaluate those functions in different ways, and some of these tasks involve operations like exponentiation, but some of these tasks are pretty simple, such as finding the sum of numbers when it comes to figuring out the degree of a polynomial. When it comes to expressions, it comes crucial the ability to factor a polynomial, and as you know, it is not an easy task. So you have to be able to factor as much as possible, and you have to be able to distribute and combine like terms. So those are the common pre-algebraic tasks when it comes to polynomial expressions. Now, frequently you may have to deal with polynomial equations when working with polynomial functions. So you should be able to solve polynomial equations. And the rule for solving polynomial equations is that we always solve it by factoring and then using the zero product property. So again, your ability to factor is crucial when it comes to working with polynomial functions and polynomial equations, and vice versa. Now that we completed the conversation about the prerequisites, let's start answering these questions. And first, let's talk about different forms in which polynomial functions can be written in. And there are two main forms, standard form and factored form. You should know how to go from one to another when possible. And you should know the corresponding vocabulary. So you should know the meaning of the words such as leading coefficient, degree, free coefficient, multiplicity, root, and so on. Now, the simplest polynomial functions are of this form. So pretty much everything is set equal to 0 except a sub n. And this function is called a power function. And power functions are pretty much the simplest polynomial functions. So that means you should know everything, and I mean everything about them. So the graph of a power function depends on not just the graph and the properties of the power function depend on the sign of the leading coefficient a, so whether it's positive or negative, and on whether the power is even or odd. So when n is even, a is positive, this is the graph you get. So it's kind of parabola looking when n is 2, but as n increases, it gets sharper, like steeper. And it is not called parabola anymore. Here on the left, you can see the properties of all of this, all of the properties of this particular example. An important one here actually is to remember that when n is even and a is positive, both ends are opening up. When n is odd, a is positive, the right side goes up, the left side goes down. When n is even and a is negative, both ends go down. And when n is even, a is negative, right side goes down, the left side goes up. So it shouldn't be too hard to remember the relation between the sign and the graph. So the right side always goes in the direction of a. So if a is negative, the right side is negative. And n means whether the both ends behave the same or the opposite way. So if n is even, they both do the same thing. If n is odd, they do the opposite. And once you understand that, answering all of these questions is pretty straightforward. It's just visualizing the graph and pretty much just reading the properties of from it. Now, when it comes to graphing polynomial functions in general, it comes in stages. We learn bits of information from two different forms. From standard form, we'll learn the end behavior by looking at just the leading term, and leading term is now a power function, and we just said that we know everything about power functions. So power function made of the leading term of a polynomial function represents the end behavior of that polynomial. So here's the table that briefly summarizes that. Now, the local behavior around those x-intercepts we'll learn by analyzing the multiplicities. So when multiplicity is even, the graph bounces. When multiplicity is odd, the graph crosses right through it. Believe it or not, this is enough for us to sketch a very decent graph of a polynomial function following the steps. Determine the end behavior from the standard form, determine the local behavior from the factored form, and sketch the graph according to these patterns. Trust me, there is only one continuous line that satisfies all of these conditions, and you should be able to figure it out. Again, I'm not here to re-teach you all of this. The format of this review doesn't allow me enough time for that, so if you need more details or examples, let me know in the comments. Now, with the graph in front of you, you should be able to figure out the domain and range. The domain is always, because of the nature of polynomial functions, in particular the lack of constraints, the domain is always all real numbers. Now, the range of a polynomial function with odd degrees, with odd, not degrees, with odd, I guess it's degree of a polynomial is all real numbers. For some reason, I was thinking degrees of freedom from statistics. So if degree of a polynomial function is odd, like this example, it ranges from negative infinity to infinity. If degrees are even, then it has to reach its max or mean, and the actual conversation about how to find that mean or max is something that we'll spend more time doing in calculus, not algebra. It's not as easy as it is for parabolas. Intercepts. We do find y-intercept by plugging in x equal to 0. In standard form, your y-intercept is the free coefficient. In factored form is the product of the leading coefficient by r's raised to, it's actually not r's, but I should also throw here the -1, right? For some reason I forgot about that one. And here we put n1 plus plus n. Right, so it could be negative. And but again, we're not here to memorize this formula. We're here just to remember that the y-intercept is the output when x is equal to 0. On the other hand, the x-intercept is the input when the output is equal to 0. So to find the x-intercept, we have to set it up as a polynomial equation, and to solve the polynomial equation, we have to factor it. So even if the polynomial is not given to you in factored form, to find the intercepts, you have to factor it. Once you factor it, the solutions of this equation are your x-intercepts. Again, here's a reminder that your ability to factor is something that we develop in not even pre-calculus, pre-algebra, but factoring in general is not easy. Even though we try to learn it early on, it's not an easy task. Now, when it comes to asymptotes, polynomial functions do not have asymptotes. Polynomial functions are continuous in their entire domain, from negative infinity to infinity. Now, your ability to determine monotonicity of a polynomial functions depends on your ability to find the minimum and maximum, which is something that we focus on in calculus. However, one thing that you should know is that polynomials of degree n may have up to n-1 turning points. So for example, it's impossible for polynomial with degree 5 to have 7 turning points. So this rule kind of, you've seen this rule before. Parabola is a polynomial of degree 2, so parabola, according to this rule, has at most 1 turning point, which we call vertex. Cubic graphs can have at most 2 turning points. They may have one, I guess they may not have 1 turning point. They can have 2 turning points or no turning points, but they cannot have 1 turning point. So the number of turning points, if it's not this, it has to be some even number different from this estimate. All right. In general, polynomial functions are not one-to-one, and therefore, in general, they may not have an inverse. However, in some special cases, they do have inverses. So when you have these special functions, you have to be able to find the inverse following this standard procedure. That is, you write your y as a function of x, you swap your input and output, and then you isolate y. Sometimes it's easy, sometimes it's not, but you should know that this is the process that we have to do when looking for the inverse functions. Now, when it comes to symmetry, in general, polynomial functions are unlikely to have symmetry. However, if it happens, you should be able to figure this out analytically using the definition of an odd function being such that negative sign can be factored, and of an even function being as such as the sign kind of is absorbed by the function. But in general, again, it's very unlikely that some random polynomial function will have a symmetry. Now, what are some special features of polynomial functions? Remember, every function has something special about it, which is one of the reasons why it is worth being studied. Polynomial functions are known as very flexible, continuous, smooth curves. So that means if you give me any number of points, so give me like 1,000 points anywhere, as long as they don't sit on the same vertical line, you can give me very large number of points, and I can find you a polynomial that goes through all of those points. It's going to be like a nice smooth curve, and we can find the equation of it. It will be a polynomial function. So they are very nice smooth curves, which makes them very special. Now, if you need to find an equation of such polynomial function, again, for a polynomial function of degree n, so polynomial function of degree n has n plus 1 parameters. So why? Because look at the quadratic functions. Quadratic functions have polynomial functions of degree 2, but they have 3 parameters. If you look at cubic functions, they are polynomial functions of degree 3, but they have 4 parameters. So to find an equation of a polynomial function of degree n, you have to be given n plus 1 points. Once you're given those n plus 1 points, you set up a system of n plus 1 linear equations in n plus 1 variables. Your variables here will be the coefficients, and we are pretty good at solving systems of equations by now. So this is what it takes to find an equation for a polynomial function. Now, when it comes to applications, as I said earlier, again, from the practical point of view, rarely you have to work with a polynomial function of the degree higher than 3 or 4. But they are nice, and they are generalizations of parabolas and cubics and so on. And they, like, graphing them actually allows us to develop and practice analytical skills. And that's why polynomial functions are important. So this was a brief review of polynomial functions. Again, its purpose wasn't to teach you everything that you missed in algebra or precalculus, but to just give you a brief review. If you need more details on any of the slides, please let me know in the comments.